This video is about the method of partial fractions for integration. As always, begin by reading through the textbook and taking some careful notes, but now consider the following highlights for this topic. We're going to recall, first of all, that this method of partial fractions decomposition is not new. In fact, this is typically part of a Precalculus or college algebra course, and so I'm not going to be teaching that particular strategy from scratch. However, I do have several other lectures that I will link. If you have access to this blank notes file, then these should be actual links. But if you don't, I will try to put them in the video description below, just so you can refer back to those. Those will be a more thorough treatment of, with more examples of just those partial fraction decomposition steps in the four cases that you'll come across. But now, in some cases of rational functions, we will do partial fractions. So that skill that was previously taught in a more introductory course, that will be now used to do partial fraction decomposition on an integrand in order to integrate it. So that's kind of now the purpose or use of partial fractions decomposition as a skill. Now, there are a few steps we want to keep in mind, and we'll practice these with some examples shortly. First, if the rational function is improper, that is, if the degree of the numerator is higher than the degree of the denominator, then we're going to use long division first to simplify it. So we'll see an example of that shortly. That's good to catch because it changes the problem immediately to something more easily handled. Secondly, if we've even done step one, sometimes it doesn't apply, but secondly, we're going to factor all denominators completely. And then thirdly, we're going to proceed with the partial fraction decomposition. Again, this goes back to those previous lessons, but we'll see it done here as well. I'm going to go through those steps in these examples as needed. And then lastly, or fourthly, we're going to integrate decomposed terms using known integration methods. So anything you know about integration so far might be used, and that's the kind of the point here. But we'll see how the decomposition actually helps us get to a place where we can use them. But then another note to put in here is that trig sub integration, which was our previous topic, may also work in some of these cases. We'll just have to see. And ultimately, when you're doing integration in general, you're sifting through your tool bag to find out which tool applies and which is the best to use. You might sometimes have a couple options. Our first example is given as this. We want to find the integral of, this is an indefinite integral, of a fraction whose numerator is 5x plus 1 and whose denominator is the product of two binomials in parentheses. We have 2x plus 1 times x minus 1. And then this is all dx, of course. Now, in order to integrate this, again, you can sift through any tools you now know. You can, maybe expand the denominator if you'd like, just to see if that gets anywhere. Try a u sub. It may not get anywhere useful. And so I want to demonstrate that this method of partial fraction decomposition might be fairly useful here. To do this method, we're going to start. Our first step in partial fraction decomposition would be to factor the denominator, but in this case, it's already given as factored. So we don't need to do that. We can just use it as given. So we'll do the step of taking the integrand. In this case, I'm going to rewrite it over to the side as 5x plus 1 all over the product of those two binomials, 2x plus 1 in parentheses times x minus 1 in parentheses. And we're going to set that equal to the kind of general framework of our decomposition. This goes back into those details of how to break this down and referenced in those previous videos above. In this case, we have two distinct linear factors. All right, so depending on what your denominator is, it determines how to set this up. And therefore, we're going to write out the decomposition as the following. I'm going to write it as two fractions. The first one, I'll just put a numerator as a, and I'll put the denominator as the first factor, 2x plus 1, that we had in our factored denominator. But then for the second factor of the denominator, we need a second fraction, and then we'll put that one as a b over the x minus 1. So obviously the point here is we don't know what a and b are yet. We're going to find those. And the process of decomposition allows us to take the original integrand and break it into, or break it down into, decompose it into fractions that when added would give us that original integrand. So let's get that process going. We'll do at this step what you typically would do, which is try clearing fractions. To clear the fractions, of course, we would need to think of this as having an LCD, which would be actually the original denominator of this problem. It'd be 2x plus 1 in parentheses times x minus 1 in parentheses. In order to clear the fractions, we're going to multiply by that on both sides. Now to do that, on the left side, if you multiply by that LCD, of course the entire denominator will end up canceling with it because, well, it matches, right? So you'd end up with the following equation: 5x plus 1, the numerator of that left side, the original integrand here, and that would equal, now on the right side, if you're clearing the fractions by multiplying by this LCD, you should end up with no more fractions. So notice in the first fraction with the denominator of 2x plus 1, that would cancel with the first factor of our LCD, leaving us with the a in the numerator times the factor that wouldn't cancel, which is the x minus 1. Moving on to the next fraction, again, if we're multiplying all the way through to clear these fractions by this LCD, we would have the plus sign in between those fractions. And then in a similar way, for the second fraction, the x minus 1 would cancel with that denominator. So that factor is now gone, leaving us with a b that we had in the numerator times the 2x plus 1, which would not get canceled when multiplying by that fraction. All right, so at this point we have the first step completed, where you're just clearing the fractions algebraically. As recalled again from those introductory lessons above, the next step would be to try distributing or expanding everything we have. So I'm going to rewrite this as 5x plus 1 equals, if I distribute the a, we'll end up with a times x minus a, plus distribute the b, and we'll get b times 2x plus b. Now, remember, the goal here to get the decomposition done is to figure out what a and b are. And in some cases that are fairly simple, this being one of them, there's not a whole lot of work needed. So let's see how that turns out. If I just keep going, copying down my equation as 5x plus 1 equals, but then I collect or combine the a terms that I have in this previous step. So I'm going to write them next to each other as ax plus b times 2x. Okay, again, those are just those terms that involved the x in that previous step. But then the other terms that involved not the x, so we had a negative a and a plus b. I'm going to put those down as well, but collect those together. Why am I doing it that way? Well, as you may recall, then I'm going to rewrite this one more time. And it's convenient because I can factor the x out of those first two terms. But I'm going to do that by writing the x after it, just as a little visual aid here. Of course, we usually factor things out in front of a set of parentheses. I'm going to put it at the end here. So I have a blank set of parentheses, which would contain those first two terms, but with an x factored out. That would turn into just a plus 2b. Again, I'll reorder some of the way I've written this just to look more familiar. Usually we write the constant factor in front of a term, so I'll just put the 2b there. So now we have a plus 2b in parentheses, and then after it times an x. That's just the x being factored out of those two terms. Okay, carrying on then, we have a minus sign between the next terms. I'm going to just keep that. And if you think of those next two terms, which are simply a plus b, of course it was a negative a plus b, if you think of those as just a constant term, then everything will line up as needed. So I'm going to just copy them down in that simple form, just minus a plus b as we had them. But there's a slightly visual, easier way to write it, which is instead of putting the minus a, since we're ultimately looking back, if you look back at our original decomposition framework, we wanted a plus between these two fractions. So in order to get that in the picture, instead of doing the minus a, I'm going to do this as a plus, and then in parentheses I'll put negative a plus b. It's equivalent, but it lines up a little bit more closely with our target setup above. Okay, now again, I said this was a simpler type of setup, and that is true. If you now look back at where we are, or look at what we have now, and look back at the equation as a whole, let me highlight a couple things here. So you'll notice that a plus 2b is, you could say, our coefficient of x. But then if you compare that to the left side of our equation, 5 is the coefficient of x on the left side. Therefore, those must match. This, again, is a simple form of partial fractions, but it's a nice one to start with. Or, secondly, if you look at the everything after those terms, which would end up being the constant term, we put them in parentheses as adding negative a plus b. That must then match up with the other constant term on the left side, which must be that plus 1. So that's the general idea. Again, in the simpler case, things just line up so nicely like this. They won't always, and we'll be able to figure out how to get around those other situations. But for now, all we have to do is say this: a plus 2b must be equal to 5, and negative a plus b must be equal to 1. So it gives you really just a system of equations where a and b are your variables, and it's just plucking out what we identified as matching in this previous step. Now, with this basic system of equations, you can just use basic algebra to solve it. So I'm going to pick on that second equation in our system here, negative a plus b equals 1. If you add a to both sides of that equation, you end up simply with b equals a plus 1. And if that's the case, you can plug that into the first equation, which I will now bring down to use. That equation said a plus 2b, but instead of b, we can write what b now equals, which is a plus 1. And that was all equal to 5. So we're just doing some basic substitution method for solving a system of two linear equations here, nothing crazy. If we now do this, notice a is the only variable left, so I can distribute the 2 to end up with a plus 2a plus 2 equals 5. Well, this is going good places. We could say now 3a plus 2 equals 5. If I subtract 2 from both sides, I'll get 3a equals 3, which of course tells us that a must be equal to 1. So that is one of our decomposition variables. Remember, we're going for a and b to figure out what these fractions should end up as. So we now have a, which means b has no chance. We can easily find it by now just plugging it back in to the equation we had already solved for b. So we'll say b equals, it was a plus 1. Well, if a is 1, then it's 1 plus 1, which means, of course, b equals 2. So now we have them, a and b. Again, this is a fairly simple case of partial fractions. If you go back through those introductory lessons, you'll find much more complexity, and we're going to get to some of that in these later examples in this video as well. This is just kind of getting us going. All right, if we know what a and b are, then we're going to rewrite our original integrand in terms of the decomposed fraction that we just figured out, including those numerators. So let's do this. I'm going to copy the original, actually not completely copy it. I'm just going to say that the original integrand equals now the integrand of, we had two fractions that were being added. I'm going to put those in place. The first one had a numerator of a. Well, we just figured out that that a is actually 1. So I'm going to put 1 in the numerator of that first fraction. Its denominator was 2x plus 1, so that's going beneath it. And its numerator for the second term, so plus, the next one was b over x minus 1. Well, we just found out that b is 2. So 2 over x minus 1 is our second fraction. And what we now have is a decomposed version of the original integrand. Now, why? Well, because this one's much, much easier to integrate. So we'll do that next to finish. Now you can see the purpose, one purpose of this fraction decomposition. Of course, we'll reach back into our integration toolbox of some more basic things, right? These are just simple functions that you can integrate using basic rules. 1 over 2x plus 1, you may argue, is not simple. You could use a substitution for that. That's fine. But the second term is even simpler. So we're going to rewrite these using integration rules. You would end up using a natural log to integrate these simple rational functions. Here, a natural log of the absolute value of the denominator, in this case, of the first fraction, 2x plus 1. But, again, if you were thinking back, you could use a substitution here, or just think ahead. If you were taking the derivative of this term, it would end up being 1 over 2x plus 1, which is what we're expecting. But then you'd be multiplying by the derivative of that 2x plus 1, which is 2. To cancel that out, we have to throw a 1/2 in front of this term. So actually, the antiderivative is 1/2 natural log of the absolute value of 2x plus 1. And again, a substitution would be a more robust way to take care of that, a 1/2, but I don't think need to go that route. Moving on to the second term, again, this constant numerator of 2, you could just float out in front of the integral, and then that would leave us with the natural log of x minus 1, and this one's even simpler because the derivative of that denominator would be 1, which wouldn't change anything else, so we'll just leave it as 2 times the natural log of the absolute value of x minus 1 as our second term, and then, of course, don't forget the plus c for our constant of integration, and that should do it. We've now then used partial fractions to decompose the original integrand and end up with something that was doable pretty easily with previously known methods. All right, our second example is this. We're going to find the integral of a fraction whose numerator is x squared and whose denominator under that is x minus 1, and this is all dx. So again, you'll notice a rational function setup here, which may cause you to think of partial fractions, but I want to note that as we did above, one of the first steps, even when doing partial fractions, is to say if you have an improper integrand or fraction, you can just do long division first. So this is what's called improper. Why? Because the degree of the numerator happens to be higher than the degree of the denominator. Improper technically means higher than or equal to, but in this case it's higher, so we're going to do long division. Long division. This would be one way to take care of this. There might even be another way to do a substitution to handle it, but I'm going to go with this, demonstrate this method. Long division means you're going to take your denominator x minus 1 and set it up in the long division setup where you have this little like roof over. So you have the divisor on the outside, the left side of the roof, and then underneath the roof you have the dividend, which is the numerator. In this case it's x squared, but then you'd have to fill in the missing term of x to go down. So I'm going to put a plus 0x, and then you could even fill in the missing constant term as plus 0. Again, see basic intermediate algebra even for long division. Reminder there. If we do long division, we're going to say, okay, x, the first term on the outside, times x will give us the first term on the inside. So I have an x on top of my roof now. I multiply that back through the divisor to write the result underneath. In these like terms, I'll have x squared minus x, then lining up those like terms. And now I want to subtract ultimately, which means I'm going to change the signs of these and then add. So the first terms cancel. The second terms, which, by the way, those first terms were an x squared minus an x squared. The second terms lined up vertically are 0x plus x. Well, that's like saying 0 plus x, which is just x. So we have an x result beneath it. Bring down the next term, which is really only a 0 to hold the place for us. And now we start over. X times a positive 1 will give us x. And then we multiply back through with that 1 to the divisor terms, giving us x minus 1. Now we change the signs and add again to subtract. The x minus x will cancel. Those vertically line up. And then we have 0 plus 1, which of course is just 1. Now, that 1 is the remainder, and typically this would happen in long division. Well, what's nice about what we have as the result is the following. I can turn this original integrand into the following. So the numerators are now going to be, or the terms are now going to be x plus 1. This is just coming directly. Let me highlight this. Get lost. So this is x plus 1 coming directly from the result of our long division. But the result of the long division would also include the remainder. So that would be plus 1, the remainder, over the original divisor of x minus 1. And then we shouldn't forget our dx. So, all right, let me even highlight that remainder so we know where that's coming from. So this 1 is our remainder, but it shows up in our integrand. Now, why is this helpful? We'll check out how much simpler those terms are. In fact, these are just easily integrable by now. So the integrand, the antiderivative of x would be x squared over 2. The antiderivative of 1 would be x. And the antiderivative of 1 over x minus 1 would be the natural log of the absolute value of x minus 1. Again, we kind of reviewed that little natural log antiderivative in the previous example, and then we'll say plus c for our constant at the end. Our next example is the following. We have the definite integral this time, so it's from 0 to 1, given with those bounds, lower bound 0, upper bound 1. The definite integral of the fraction whose numerator is x squared minus 1, and then under that, the denominator is given as follows. There's a set of parentheses containing x plus 1, and those are squared. And then next to it, we're multiplying by another set of parentheses containing x plus 2. And then this is all dx. All right, so again, we're going to try the method of partial fraction decomposition on this one. Obviously, in its current form, nothing else will work conveniently. You can try other methods. Sometimes you'll find other things that are possible, but in this one, I want to go with this partial fractions method. In order to start that, of course, we'll factor the denominators, but they're already, in this case, the denominator is already factored. So what we're simply going to do is rewrite this in its decomposed form. So let me write out the original, which is x squared plus x plus 1 all over, in this case, x plus 1 in parentheses squared times x plus 2. Just copying this original integrand down, but we're going to set this equal to now its general decomposed form. So notice, though, in this case, we have a repeating linear factor. So again, review those partial fractions introductory videos as needed. When you have a repeated linear factor, you have to use a couple terms to, in this case, handle the repetition of squaring. This was a squared linear term. So what we'll do is this. I'm going to put a constant numerator a over 1 power of that repeating factor x plus 1. But then I have to put another fraction, so plus, I'm going to put a constant term of b above the second fraction, but then the denominator it will be the squared version of that repeated linear factor. Again, review those partial fraction intro steps as needed. But then, of course, we still have another factor to deal with, so our third term will now have a c in the numerator over an x plus 2. All right, so that's our basic setup. Of course, the next steps will be similar. We're going to clear the fractions. So our LCD, in order to clear these fractions, will be basically the original denominator. So x plus 1 squared times x plus 2. And if I wanted to clear the fractions by multiplying by that all the way across, again, I'm not showing all the detail of that here, but that's just some basic algebra. We'll end up with, on the left side, the numerator we had, so x squared plus x plus 1. The denominator under it would cancel completely with that LCD. But then moving on to the right side, we'd have in the first fraction, of course, there's an a in the numerator, and then the x plus 1 under it would cancel with one of the x plus 1s in our LCD, but not both. So we'd end up with an x plus 1 in parentheses times the x plus 2, which of course did not get canceled either. Moving on, then our next term would have a b in the numerator, which was its numerator, but then the x plus 1 squared in its denominator would cancel with the x plus 1 squared that's in the LCD, leaving behind only an x plus 2 in parentheses after the b. And then moving on to our last term, when clearing these fractions, which was a c on top, which I'll copy down, and then under it was an x plus 2, but that would be canceling with the x plus 2 in the LCD, leaving us only with, in parentheses behind the c, an x plus 1 squared. Okay, so that's just clearing the fractions. Now at this point, again, it looks like there'd be a lot of work to do if you want to go the route we took in the previous example, where you expand the right side completely, line everything up with all the terms on the left side. It may be possible to do that for this one, but I want to show the maybe shortcut method that you can use during partial fraction decomposition that I think is just a lot quicker in this case. If we were to let x equal, I want to pick something that would cancel out a whole bunch of this equation. You'll notice a lot in this first term where we had a times x plus 1 times x plus 2. If I pick an x value that will drop that entire term out to 0, but not the other terms, or not all of the other terms, that is, then it can be very convenient. So if I pick x equal to, let's say, -1, again, you can review this in those more intro videos linked above, but why would I pick x equals -1? Because that would, notice in this first term with the factor of x plus 1, that would turn that into a 0, which would drop out that entire term, but it would not drop out the middle term where we had b times x plus 2. Now it would also drop out the last one to be a 0, but that's actually okay. So if I had x equal to -1, my entire equation would turn into a -1 squared. I'm going to start all the way with the left side. So -1 squared plus -1 plus 1. That's just the left side of our equation. And that now equals the right side, but the first term, as mentioned, will drop out to a 0. Then we'll have plus b times, in its parentheses, if x is -1, it'd be -1 plus 2, because it was just x plus 2. And then the last term, the c times x plus 1 squared, again, if x is -1, that would turn into a 0 as well. So if you can pick a value for x that eliminates some, or drops out to 0, some of your terms, but not all of them, and it leaves one of your variables, in this case b, to solve, then it's useful. So let's finish this out. This is, if I kind of go back through and simplify, -1 squared is 1, -1 plus 1, that'll get even better, equals, on the right side it's going to be a b times a, in this case, -1 plus 2 is 1. So if I simplify even more, 1 minus 1 on the left side here plus 1 will be just 1 equals, and then b times 1 is b. Well, what do you know? We already know the value for b. So that was a quick way to find it, but notice we don't know a or c yet, so we can do this kind of again, the same process here, but pick a different value for x that would not eliminate, let's say, the c, but maybe would eliminate the a, or something of that type. So I'm going to pick on, let's see, what value would eliminate the a but not the c? If you look back up, -2 I think would do that. Now you'd say that eliminate the b also, but we already know b. So we're going to write it this way. If x equals -2, we go back through the entire thing. That means we have -2 squared plus -2 plus 1. That was the left side of our equation. Now moving on to the right side, we have a, which we don't know yet, equals, and then in its parentheses afterward, if x is -2, we'll have a -2 plus 1 times a -2 plus 2. Well, that's going to be a 0, and that was kind of the whole point of doing that. So in fact, I'm going to write this whole thing out as just a 0. That whole term would turn into a 0. Then moving on to the next part, we had b times x plus 2. Well, we already know that b is 1. So once you know a value, you can just kind of use it from there. We know that b is 1, so we're plugging that in for b, times x plus 2. Well, -2 plus 2 would be that term. And moving on to that, or after that, we have plus c times, in parentheses after it was x plus 1. Well, if x we're supposing right now is negative 2, that's a negative 2 plus 1, of course, being squared. Notice what that does. It gives us an equation that we can use to solve for c, the only variable that would be left. So let's do that. We'd have a 4. If I start over and simplify 4, was negative 2 squared. 4 minus 2 plus 1 equals, we had 0. We'll just leave that as nothing. And then there'd be another 0. So 0 plus the second term is also 0 because of the negative 2 plus 2 factor in it. And then plus c times, well, negative 2 plus 1 after it would be a negative 1 squared is 1. So it's really just c times 1, which is c. So this is looking good. We have, if I start over again, 4 minus 2 is 2, plus 1 is 3. So we got 3 equals 0 plus 0, which is 0, plus c. So what do you know? We have c just like that. Now, in order to find a, which we also need, right, we need a, b, and c to fill in this original setup we have above. So in order to find a, notice we know everything else. We know b, we know c. You can pick any other value for x. We'll do the same kind of method. All I want to do is pick a value for x that will not drop out the entire first term that includes our a. So I'm just going to pick on something simple, like what if a were 1? Right? Well, then, I'm sorry, x were 1. I'm going to pick a value for x here that will not drop out that first term. If x is 1, going through the same process, let's see, the left side would be, of our equation, would be 1 squared plus 1 plus 1. And then I'm just plugging 1 in for x in this equation we have after clearing the fractions above. That would equal a times 1 plus 1. Just plugging that in still, times 1 plus 2. Plus, now we already know b, so we'll just plug that in as 1 times, and then x plus 2 was after the b. Well, that'll be now a 1 plus 2, because we're using 1 for x at this point. And then moving on, we also know c is 3, so I'll put a plus 3 times x, which is now, we're supposing 1, so 1 plus 1 squared. Okay, well, the value we have now is that we have an equation with only one variable, and that is a. A little bit of detail here to figure it out, but I think you could do so. Go ahead and try that. Well, I'll write out some detail. This would be 1 plus 1 plus 1 is 3 equals, after the a we have 2 times 3, that's 6, so we have 6a, plus, moving on, we have just 1 times 3, which is 3, plus, at the very end here, 3 times 2 squared is 4, 3 times 4 is 12. Okay, so we're trying to just solve for a here. Again, combine terms and do so. 3 plus 12 is 15. If you subtract that from both sides, we'll get a equals, I think, a negative 2. Double check that to make sure you're confident with it. But that's all we need to do to find the value for a. Well, now we know a, b, and c, which means the work for partial fractions is done. Now, we haven't done the calculus part of this problem yet. We're getting to that. All we had to do, though, first was figure out what these partial fraction values were. Sometimes this process can take a little bit of time, as seen in some of those, again, previous topic examples for partial fractions. So now what we're going to do is go back and rewrite our original problem. So let me do this. We have now the integral, and it was going from 0 to 1 originally. I'm just copying those bounds down. But we're going to use the decomposed version of this integrand, which we now have figured out thanks to knowing a, b, and c. So what I'm going to do, actually, I'll be a little bit lazy and just copy this over, but we need to take the decomposed version that we had, which was written in terms of a, b, and c originally, and we're going to bring that down and put that in our integrand, but then we're going to be replacing the a, b, and c with what we now know they are equal. So instead of a, I'm going to put a negative 2. Let me write this in here. So we now have negative 2 over x plus 1. for the a, I'll take out the parentheses in the x plus 1 to make it look a little better. The second term was plus b over x plus 1 squared. Well, now we know that b is actually just 1. So instead of b, we're just going to write that as a 1. And then instead of c, for the last term being c over x plus 2, we found that c was 3. So we'll make that 3 over x plus 2. And this is all dx. Again, the whole value of this is that now you have an integrand that can be solved fairly easily knowing some basic integration or antiderivative rules. You know what, to be extra clear, I should be putting this all in brackets. So I'm going to put a bracket around everything we just wrote and also holding the bounds, which is a possible way to write that. So we'll do that. Take note, I mean, if any of this, this is just basic integration antiderivatives here. So this middle term may be less obvious. If you want to do a substitution on that, just to double check it, you could, but that should be working out that way. And then, of course, you'll do the fundamental theorem of calculus by plugging in 1 first to this entire expression, and then subtract the result, plug it in 0. I'm going to do a 1-2 skip a few on this, but check the result. You should end up with 1/2 minus 5 natural log of 2 plus 3 natural log of 3. And again, we get a value without the c because it's a definite integral. Or you could say another form, if you want to simplify that even further, you could say that's the same thing as 1/2 plus the natural log of 27 over 32. Another valid answer, just doing a little bit more simplification there. But ultimately, either answer is okay. All right, our next example, number 4, is given as the indefinite integral of a fraction whose numerator is 10. And then under that, the denominator is x minus 1 in parentheses times x squared plus 9 in parentheses. And so again, you'll find that a substitution doesn't work well here, a basic one that is. So let's try a partial fraction decomposition. And in order to handle that, we're going to take this original fraction. I'm going to copy it down, kind of like I've been doing, because we have to set up the initial decomposed framework. But this one has something different we haven't seen yet, and that is we have a non-linear denominator factor. So the first factor, the x minus 1, being linear, can have a constant numerator. So we'll just say a over x minus 1 as our first fraction. But then we're going to add for the second one, since that denominator factor is x squared plus 9, and that is not factorable. It's an irreducible quadratic factor. And because of that, we have to make the numerator linear. So we're going to call that bx plus c. Again, review those intro videos on partial fractions for more examples and work on this. But that's the necessary rule for these types of denominators that are irreducibly quadratic. All right, I'm going to move a little bit quicker on this one now since we've seen some of these things already. But if you figure out the LCD, which is the original denominator given, that's the LCD. And if you clear the fractions with that, we should end up with 10 equals a times x squared plus 9 plus bx plus c in parentheses times x minus 1 in parentheses. And after clearing those fractions that way, if we then move on to our method as demonstrated previously of picking convenient values for x to substitute in here, instead of expanding everything and going that route, which is an option, you could also just pick these convenient values. So like, let's say x is equal to 1. Notice that would drop out because of the x minus 1 factor. That would turn it into a 0 and drop out all that's with it, giving us a value of way to solve for a. So we'd end up with 10 equals a times, if I plug in 1 for x, I'd have just 10 after the a. X squared plus 9 would be 10 if x is 1. And then plus, everything else would be 0 because of the x minus 1 factor when x is 1. Which means, of course, pretty simply here that a must be 1. We already have our first value. Well, in order to find anything else, you already know a, which means you can now reuse that. I'm going to rewrite down, but suppose x equals, let's think about this. So with what's left in that entire second term, I want to be able to drop out one of the two variables, the b or the c, but not both, right? If I let x be 1, obviously both dropped out. That was helpful for finding a, but now I want to find out one of those other ones. If I let x equals 0, then the b term will drop out, but not the c. And that's actually a convenient setup to have. So let's proceed that way. I'm going to write out our equation 10 equals. Now we know already a is 1, so I'm going to put that in. 1 times 0 squared plus 9 would be 9. Plugging in 0 for x here at this step. Keep going, plus, after in parentheses, b times 0, well that drops out to be 0, plus c. I'll just write that as c, times 0 minus 1 is negative 1. So we should be able to solve for c here. Let's do that. 10 equals 9 minus c. Well, if we just kind of add c to both sides and subtract 10 from both sides, we should end up saying then that c equals negative 1. And if that's the case, we should be able to find b, because we have a and c. So again, I'm going to just skip a little bit of those steps here. You can plug in anything you want for x, because now you know a and c, and then kind of rewrite your equation. You should be able to solve for b, like pick x for something else simple, negative 1, 2, something like that. Anyway, b should end up being negative 1 in this one, if you follow those same kind of steps to get that. All right, so we should be ready to put this all back in place. So I'm going to go back and rewrite our integral. And now in the decomposed form, plugging in the a, b, and c's that we've found, we should have our first term in the integral as 1 over x minus 1, and then plus the second term, which, remember, we had this linear second term because of our quadratic denominator. So when plugging in the b and the c there, we should end up with a negative x minus 1 over x squared plus 9. And this is all, of course, dx. Well, that's more convenient because now we can split this up and hopefully evaluate this more easily. Notice the second term, this fraction, has a numerator that is 2 terms. So actually, it'd be convenient to split that even further. I'm going to write this as 1 over x minus 1. And then actually, I'll make it a minus x over x squared plus 9. That's just kind of splitting up this second fraction. And then minus 1 over x squared plus 9. That'd be using the second term of it as its own fraction. And then that's all dx. But the good news is that those are all very doable integrals. So let's finish this off. We should end up with the natural log of the absolute value of x minus 1 minus 1/2 times the natural log of x squared plus 9. There's maybe a little work there you'd want to do with a substitution to get that second antiderivative there. And then lastly, minus 1/3 times, this is a standard, be careful on this one. Let me put this in a different color because this, I'll write it out first and then I'll just note it. So this would be 1/3 times the arctangent of x over 3 and then plus c. So this right here, this last term, be careful, that would be an arctangent using the formula for it. That's like saying 1 over x squared plus 3 squared. If you think back through the antiderivative for that, or think of the derivative for arctan, maybe that's easier to go that way. You'll find that to be a standard formula, but there we go to finish off that integrand. All right, our next example, number 5, is the indefinite integral of a fraction whose numerator is x plus 4 and whose denominator is x squared plus 2x plus 5. All right, so now with this one, notice it's definitely a rational function where the numerator and denominator are polynomials as given, but I want to point out a couple things to notice here. It's good to be thinking through really a large number of tools you hopefully have in your tool bag at this point. And one of those tools is just a basic U substitution. Now, this one doesn't quite line up perfectly for it, but I just want to notice here that this denominator has a derivative that is close to what we're seeing in the numerator here. So just kind of notice that. This is something to look out for. I'm going to suggest then the following. We're going to take this and split it up. I'm going to rewrite this as the integral of, and I'm going to split this up to make it a little bit more convenient. Keeping the denominator as x squared plus 2x plus 5, of course. I'm going to write the numerator as x plus 1 first. But then we're going to split that, of course, dx. But then we're going to have to add that to another term to make this splitting up into two integrals with what's left. Well, notice the numerator I split as x plus 1, but I had originally an x plus 4. So obviously I have to keep the other value of 3 around. I'm going to put that as the numerator of my second term, and then keep it as x squared plus 2x plus 5. Now, okay, is this partial fraction decomposition? Well, it's not a thorough form of it, but it's actually a way to split this original fraction into a couple other ones that are more convenient to use. Why? Well, let's take a look at what we could do next. And these are some things, again, that once you see them, you can look for them. Sometimes students say, well, I wouldn't have thought to do that, or this next step. Like, I know, I wouldn't have either, unless somebody showed me. So that's kind of the point of seeing these examples. You should be able, hopefully, to spot them more easily next time. Now, let's look at this first integral we have. This is something that should be doable for us. In fact, it's a little bit off by a constant, but notice, again, I'm just going to do a little bit of pre-thought work here. If you take this denominator, let's imagine we were going to do a substitution in this first integral, and the denominator was going to be u. If that was the case, then u would be x squared plus 2x plus 5, and then think through du would be, well, if I take the derivative of that with respect to x, it'd be 2x plus 2, and then dx, right? But notice our numerator isn't quite 2x plus 2, but it's actually not far off. So with that in mind, we can force it a little bit and say this. I'm going to rewrite this as 1/2 times the integral of 2x plus 2 over x squared plus 2x plus 5. Okay, now let that sit in a second. All I did was multiply by 2 in the numerator. Why? To get it to match what we would like for that substitution derivative. But then you can't just multiply by 2. You have to compensate by dividing by 2 to make sure nothing actually changed. It's a bit of a trick to get this to work out more smoothly. With this second integral, the one that we broke off, having a 3 in the numerator and an x squared plus 2x plus 5 in the denominator, you'll notice this one isn't quite set up for a substitution either, because of the numerator being a constant and the denominator being x squared plus 2x plus 5. That wouldn't be quite a substitution. But there's one little trick we can do here to get this looking better. I'm going to rewrite it as the numerator of 3. But then I'd like something in the denominator whose derivative would be more closely related to a constant, which is what we have in the numerator. So one trick on this one we could do is to complete the square. I'm going to do this in a different color. Actually, no, I'm not, because I wanted to kind of mimic what I just did with the substitution on the left. So I'm going to write out the denominator. Instead of x squared plus 2x plus 5, we're going to write that out as x in parentheses x plus 1 squared. Now, think about that. You know what? I'll go even slower. I'm going to write this out as x squared plus 2x plus 1, and then the plus 4 after. Now, why would I do that? Well, think about this. So that 5 is really 1 plus 4. So I haven't actually changed anything there. So that's good. But then what we're seeing, which I will highlight differently here, let's see. We're seeing an x squared plus 2x plus 1. That's a perfect square, which means we could rewrite it even more conveniently. So let's do this yet again. We have 1/2, and we're just going to copy everything down here. The first term was the 1/2 times the integral of 2x plus 2 in the numerator over x squared plus 2x plus 5 beneath it, all dx, plus here's our second integral, which now has a 3 in the numerator over, if I write this in factored form, it's x plus 1 in parentheses squared. That was the perfect square we had there. But then plus 4, and then dx. Now why? Again, because that's more convenient for a substitution, because now you could let u be x plus 1. I'll just say we're going to do a u sub for that. And then the derivative of u would be just 1, which will be a constant, and we can match it with that numerator term. Now, in order to handle such a u sub for what we're looking at in this second integral, we have to be mindful of a couple things. So first of all, let's recall that the derivative with respect to x of arctangent x is 1 over x squared plus 1. And we're not seeing the plus 1. We're seeing a plus 4. So actually that makes us a little bit sad because it doesn't quite line up. We're going to have to do a little bit more manipulation and get it to match. And we can. Just want to point that out, that that's something we can't just look over or gloss over. So that makes us a little upset. So let's now proceed. I'm going to go back and start all the way here from the left side. Copy yet again. So we have 1/2 integral of 2x plus 2 over x squared plus 2x plus 5 all dx. That's our first term integral. We haven't even really dealt with that yet, but it's not bad. We'll get there soon. It's already set up. For this second one, however, this is where we have to do a little bit more work. So I'm going to keep it somewhat as it was, where the 3 was in the numerator. But then down in the denominator, I'm going to multiply by 1/4. Okay, so here's a little trick to fix this 4 problem we have. I'll keep that 3 up there. Here's how we can fix our problem in that denominator. I'm going to start by copying it down. So it's x plus 1 in parentheses squared plus 4. But really, I need that 4 to be a 1 so that it matches our arctangent derivative, and therefore an easy antiderivative. So the way we're going to do that is simply by a little bit of arithmetic here. I'm going to multiply by 1, or well, I'll say it this way. I'm going to divide each denominator term by 4. So I guess that's the same thing as multiplying by 1/4 to the entire denominator. But of course, you can't just do that to the denominator. You have to do it also to the numerator. Let's see where this leads us. Take this down another step. Let's see, I'll be a little bit lazy here. Just copy this entire first integral term down. Keeping that over, just don't want to rewrite that, save some time. But now, in this way, if I'm multiplying by 1/4 top and bottom, I have the integral of, now the numerator is going to be 3/4. I'm just going to pull that out in front as a constant just to keep it out of the way. And then my numerator inside will be 1 on top over. If I distribute the 1/4 to the denominator, we can actually account for it in the following way. I could make that entire first term of the denominator, instead of x plus 1 in parentheses squared, watch this. I can make it an x plus 1 over 2 in parentheses all squared, which is actually then x plus 1 squared over 4, right? Because you'd be squaring the numerator and denominator, which is exactly the same as multiplying by 1/4. And then, of course, 1/4 times 4 would be a plus 1. Okay, so this now gets us into a better place where we can do a substitution to make this happen and still use our standard known antiderivative. So if I now I'm going to focus, you know what, I'll do them each. So we're going to do substitutions here. For the first integral, we're going to let u equal x squared plus 2x plus 5. Of course, that means du equals 2x plus 2 dx, 2x plus 2 being in parentheses there. And that actually will, again, replace our numerator just fine, so we'll get to that in a second. For the second integral here, I'm going to let u equal x plus 1 over 2. Why? Because that's the part in the parentheses now that I'd love to replace with u and get an arctangent out of this. Okay, so if that's the case, then let's see, du would equal 1/2 dx, right? Just do the simple derivative of x plus 1 over 2. You can split that and make it x over 2 plus 1 over 2. X over 2 is really 1/2 x. Derivative of that is 1/2. And then times the dx. The constant disappears when you take a derivative. Okay, so that's all helping to turn this into a better form. Let's take another step to rewrite these now with their substitutions in place. For our first integral, again, we've already done the work on that now a long time ago to get the numerator to be the derivative of the denominator. So if you do the substitution on that, as listed here, we should end up with 1/2 times the natural log of the absolute value of x squared plus 2x plus 5, and then plus, so that derivative, or that antiderivative is done there. We'll put our constant at the very end, right? You could do a constant with each of these or just combine that as one big constant of integration at the end. And then plus, now moving on to this next term, we did all this work to get this to be an arctangent, so let's use that. We'd have then plus. Now, let's see, be careful here. Let me add in one little note. So if I were to take, this isn't a direct match, remember I want to replace dx. So if I multiply both sides of my du equals 1/2 dx equation by 2, then that would tell me that 2 du equals dx. Now I can replace dx with 2 du. The point is there's an extra 2 that when combined with the 3/4 as the constant in front will simplify a little bit more. So ultimately that would become, let's see, you should get 3/2 times the arctan, tangent inverse, of, in this case, well, u, which we've used as x plus 1 over 2, and then plus c. Okay, so that's, let me rewrite this one more time for a couple of reasons. Number one, it's kind of crammed in there, but secondly, I'm going to rewrite this more cleanly as 1/2 times the natural log of, we don't need the absolute values anymore because what's inside them is guaranteed positive. X squared plus 2x plus 5, guaranteed positive. So we can just write this as the natural log of, and then in parentheses, x squared plus 2x plus 5, close parentheses. And then we'll finish it off with plus 3/2. Again, that's the 3/2 because the 3/4 that was previous reduced with the 2 du. So 3/2 times the arctan, or tangent inverse, either way to write that is okay, of x plus 1 all over 2, close parentheses, and then finally plus c. You have to have the constant in there, and we can just use one big constant to handle both integrals that we split up here. Okay, one more example. Last one. I know this has been a little bit lengthy, but number 6 is as follows. We want the indefinite integral of the following. The fraction whose numerator is 5x to the 4th plus 7x squared plus x plus 2. And that's all over a denominator, which is x times the quantity in parentheses x squared plus 1, and those parentheses are squared. Okay, lots to unpack here, but I'm going to do a 1-2 skip a few on the partial fractions just to save some space and time. So let's see, I'll say it this way. Partial fractions. There's a lot of work involved with that, but you can review it. Again, there's lots of resources above to go back through all that stuff and review. I'm not going to spend all the time on that here. If you do the partial fractions on this one, it should end up being the following. The integral of 2 over x plus 3x over x squared plus 1 plus 1 over the quantity x squared plus 1 in parentheses squared, and then dx. So again, I'm not writing out the detail on that, but it's doable using even the review lectures I listed above, and I'll put in the description below to get through the partial fractions on that one. But this one, even after the partial fractions, ends up with a bit more to do. So let's take a look at these terms and notice that this last term is going to have to be a trig sub integral. So I'm going to spend a moment to go through that one because the first two terms are easy, but that one's a trig sub. So let's see if we can get through that one to make sure that's making enough sense. But I'd also point out that that's not it's not obvious that this is a trig sub. So I'll put a nice little friendly question mark there, like, really? Would that actually work? Well, there's a little bit more manipulation we should do to make it work, but once it does, you'll find it to be very convenient. So I'm going to do this. I'm going to restart and rewrite this whole integral that we've already busted up in partial fractions. Of course, I didn't show all the detail, but we're starting with the integral of 2 over x plus 3x over x squared plus 1. Plus, here's how I'm going to rewrite this last term. Instead of making it 1 over the quantity x squared plus 1 in parentheses squared, in order to use a trig sub, remember we have to get a root in the picture. So I'm going to make it the following. The quantity in parentheses is going to be the square root of x squared plus 1. But you can't just make it a square root unless you compensate, right? It was just x squared plus 1 squared. Well, how could I make this expression match that one? I'd have to make it to the 4th power, right? Think of that. Multiplying the 4th power times the 1/2 power, which is really what a square root is, will give you a 2 power, which is what we had. So that all does line up or match up. I would say that's not obvious, but it's a good little trick to help us get a trig sub going. So in fact, let's pull out our trig sub models, of course, review that as needed, but this is now going to be a triangle where, remember, with a sum in between the terms in the root, that's going to be on the hypotenuse. So we'll make the hypotenuse x squared plus 1 in our right triangle, theta in the bottom left corner. The bottom horizontal side I'm going to call 1, and the vertical side on the right I'm going to call x. Again, this is just going back to our models. So see that or review as needed. Now that's going to help us out a lot though, because our expression, the square root of x squared plus 1, is in the picture, and we can use a trig function to get it. Remember our trig ratios? One of the, actually we only really need 1 in this point. Well, now we're going to need both. So we're going to have to use our ratios, first of all involving x and a. We could say that the tangent of theta equals opposite x over adjacent 1. And our second ratio, we could say cosine theta equals adjacent, which is 1, over the hypotenuse, which is the square root of x squared plus 1. And these ratios can both come into play and help us out, which we'll have to do to proceed. So let's go ahead and take those next steps, but then also do some of the other work along the way. I think we're ready to do a little bit more. So we'll make this here. The first term, the antiderivative of 2 over x, would be just 2 natural log of absolute value of x. Now, the second term, you really could do a u sub for, because it's 3x over x squared plus 1. Notice the derivative of the denominator is close to the numerator, with being off by a constant. That would be just a standard u sub. We should be able to handle that no problem. In fact, that should end up being 3/2 times the natural log of let's see, x squared plus 1. It would be in absolute values, except that's guaranteed positive. So that's just a u sub. I'm going to note that there. Just a basic substitution. You can walk through those details if you'd like. But this last one is the one where we need the trig sub. So we're going to now rewrite that as, let's see, I need more space, plus, I'm going to copy it down for now as is, and we'll kind of redo this with more space. We have the integral of x squared plus, so integral of 1 over the square root of x squared plus 1, all to the 4th power dx. We have not done that yet, but we're about to do it. So let's start over with more space. Copy down the stuff that's done. 2 ln absolute value of x plus 3/2. natural log of x squared plus 1, guaranteed positive there. Then we got to plug in these trig values to get this working. Notice 1 over the square root of x squared plus 1 is what cosine is for us. And we have the square root of x squared plus 1 within our integral, which means this is really the integral of, let's see, that denominator, if it's 1 over cosine, you could just call that secant. So we'll make that a secant to the 4th theta. That's because it's that root to the 4th power. And I should also be clear, this implies that secant theta equals just the square root of x squared plus 1, which is what we're trying to replace here. So that's now turning into a secant to the 4th. Of course, we have to keep going to get a derivative in here to replace dx, right? So we could do that with our first ratio. We had tangent theta equals x. That would imply that dx equals, the derivative of tangent would be secant squared theta, and then d theta. So that can replace our numerator. So we have now secant squared theta over secant to the 4th theta, and then of course d theta. And that's convenient. We should be able to do something with that to simplify. So let's keep going. We have 2, I'm rewriting everything here, 2 ln x, absolute value, plus 3 halves ln of x squared plus 1, plus, if we simplify this, secant squared over secant to the 4th is just 1 over secant squared, which is really cosine squared. So this is now just the integral of cosine squared theta d theta, which, if you use a power reducing, lots going on in this one, so much fun. Okay, so this, let's copy this down again. I'll be a little bit lazy on this to copy these first terms down. We have 2 times the natural log of x plus 3 halves times the natural log of x squared plus 1 plus, here we go now, we're diving in with this cosine. We're going to now make it, though, thanks to our power reducing formula, which I will recall here. This is going to be the integral of 1/2 times 1 plus cosine of 2 theta. So, a little reminder here, this is power reducing formula. Recall that, that's exactly what that is. And then, of course, d theta. Okay, let's finish this up and close this out here. So we have ultimately two ln absolute value of x plus 3 halves ln of x squared plus 1 plus, all right, so if we want the antiderivative of this trig sub integral, we should end up with a lot more to do. So you'd have 1/2 theta. I'm going to have to do a little bit more there to replace theta. Actually, let me just kind of do this now. Theta would be the arctan of x. So I'm going to do this also kind of up here in our work. If tangent theta is equal to x, then we could say theta is the arctan of x. And that will help replace what we need in our integral near the end to replace theta. So that makes this, instead of 1/2 theta, it makes it 1/2 arctan of x. All right, to be clear, what we've done so far is only covered in this last integral, the first portion of it, right? The integral of 1/2, which turned into 1/2 arctan of x because of the trig sub there. Now, that still leaves the second term, which was the cosine of 2 theta. There's a little bit more work to do for that one, so I'm going to let that just kind of be on its own for a minute and then do that next. So I'm going to write it as simply the integral of cosine 2 theta d theta, and then we'll tackle that one next. Just want to make sure to split these up clearly enough. Whoops, okay, forgot a 1/2 here. Be careful. There's that 1/2 that would have to get distributed to both of those terms. It should be in front of this last integral as well. So it's really 1/2 times the antiderivative of cosine 2 theta d theta that we'll be doing there. Okay, so let's work through some of these details to finish this off. We have 2 times the natural log of the absolute value of x plus 3/2 times the natural log of x squared plus 1 plus 1/2 times the arctan, or tangent inverse, of x, plus, now we have 1/2 times the antiderivative of cosine of 2 theta. Well, that's just sine 2 theta. So we'll say 1/2 sine of 2 theta. Ooh, I forgot another factor here. So when you're doing an antiderivative of cosine of 2x, we should end up with another 1/2 because of the chain rule. It's actually 1/2 sine 2 theta here as the antiderivative of cosine 2 theta. So that has to be there. That extra 1/2, I forgot. Make sure that's there. But now we just got to rewrite and clean this up and substitute the theta to replace it as some type of x. So we write this one more time. We have, again, I'll read it, 2 natural log of x times, 2 natural log of x plus 3/2 natural log of x squared plus 1 plus 1/2 arctangent of x plus, here we go, now we have a 1/4 sine 2 theta, but we know that there's a identity for that. Sine 2 theta is the same thing as 2 sine theta cosine theta plus c. And so we should be able to simplify that more as well. Let's see, we'll rewrite again. Notice we're going to have to replace sine theta and cosine theta, each with their equivalents from this trig sub. And we have them. If you go up and look at our model, we already know that cosine theta is equal to 1 over the square root of x squared plus 1, so we should be able to replace that with no problem. We didn't have sine theta computed, but we should be able to get it just by looking at the triangle, right? Sine is opposite over hypotenuse. So let me add this in as just like an extra little note here. We'll say sine theta. We hadn't computed it before, but now we definitely want it because we kind of came out with this identity we just used. So sine theta equals opposite, which is x, over hypotenuse, which is the square root of x squared plus 1. And that we can use to replace the sine theta we have here. So ultimately, let's see if we can put this all back together. We should have 2 ln natural log of x plus 3/2 natural log of x squared plus 1 plus 1/2 arctangent of x plus, okay, here comes the last substitution. So there's a 1/4 times a 2 is really 1/2. And then there, let's see, sine theta is going to get replaced as x over the square root of x squared plus 1. Again, we kind of just added that in as a side note there from our trig sub model above. And then cosine theta, which we knew already, would be 1 over the square root of x squared plus 1, and then plus c. Now, you could leave it in this form. I think at this point we're probably exhausted enough and call that done. Or you could slightly simplify this last term by multiplying these all together. That would be okay to do, but it's not a whole lot different.